This is the 11th session on inner product spaces. Today, in the last lecture, we talked about orthogonal complements. That is, given a vector subspace W of a finite dimensional vector space V, we defined W perp and we showed V is a direct sum of W and W perp. This is a direct sum, but each of the factors are orthogonal to each other. That's why it's called orthogonal direct sum. So we want to talk about its uses today. Okay, the first thing which we are going to do is to give a geometric proof of the Riesz representation theorem. Okay, which says that if f is a linear functional from a finite dimensional inner product space V to the ground field, then there is a unique vector V such that f of x equal to inner product of x with V. Okay, we gave a very algebraic proof. At that time I mentioned we will give a geometric proof. This proof will generalize to infinite dimensional Hilbert spaces also. Okay, and second, what we will do is that we will talk about the same kind of logic will also tell us if I have a vector subspace in a finite dimensional space, a vector outside the vector subspace, the distance between this vector and this. Okay, we will find a formula for that in terms of inner product, and we will see this is nothing other than the formula of a point alpha beta gamma to the plane ax plus by plus c z equal to d. You will learn in three-dimensional coordinate geometry. Okay, are you excited? Let's go and see. So let us get started. So let V be a finite dimensional inner product space over a field F which may be R or C. Alright, and suppose F is a linear functional to F, linear map, right? Then we want to prove this is, okay, let me call it, this is called Riesz representation theorem. Okay, at least in functional analysis it's called like that, but okay, there is a unique vector V in V said that for all x in V, f of x is given by inner product xv. Okay, we had already seen a proof. We want to see a proof which uses geometry. Suppose f is identically 0. Okay, then what is your choice of V? Obvious choice is V equal to 0, right? Okay, and uniqueness we have seen, the earlier proof also works for this, so I will not bother about that. Okay, so therefore let me assume f is not 0. Since f is not 0, then f of V must be non-zero subspace of V. Since dimension of f over f is 1, we decide dimension of f is 1. Therefore, f of V must be all of f, the field itself. Do you understand that? Okay, that means the range of f is 1. F, that therefore, okay, the rank of f is 1. And let's assume dimension of V is n. Therefore, what is kernel of f? Kernel of f, okay, the dimension will be n minus 1 dimension by rank nullity theorem. Why? Because dimension of V equal to rank of f plus nullity of f. Okay, this is n, this is 1, therefore the nullity should be n minus 1. Right? Okay. Do you understand this? Pause, review, proceed. Okay. Now let W equal to the kernel of f. We know this is a n minus 1 dimensional subspace. right? Now we also know that W perp should be dimension of that must be 1 because we know V is W direct sum W perp in particular it's orthogonal direct sum. These have dimension n minus 1, these have dimension n, therefore this was dimension 1. Do you understand that? Therefore let U in W perp, is that clear? Okay. Now suppose, okay, let us work backwards. Suppose such a V exists, right? Therefore, for all x in W, which is kernel of F, okay, f of x must be xb, but this is 0. That means b must be perpendicular to W, right? For all x in W, inner product x to W is 0, right? Therefore, where should x be? Therefore, x must be in W perp. Sorry, B. Therefore, V must be in W perp. That's the first thing, right? Now, what do I know about W perp? I know W perp is of dimension 1. So, let U be a unit vector, right? Therefore, W perp is going to be A times U. And what we saw is my V must be in W perp. Therefore, my V must be some scalar lambda times U for a scalar in the field. Do you understand this? So we for okay, to find V, what should I find? I should find what is lambda, right? Okay. Okay, pause, review, proceed. Okay, right. Now how do I find lambda? That you already know. If I want to find the coefficient of a unit vector, the idea is take inner product with that roughly, right? Therefore, lambda is lambda UU, right? Yeah. But remember, this is my V. Therefore, if this is my V, this should be U V bar, right? But U, this is your F of U bar. Do you understand how I'm working? I'm working backwards, so you may be put off. Okay, I want to find lambda. Therefore, in particular, F of U must be equal to U in a product V, but that is U lambda U, but that's lambda bar UU, which is lambda bar. Therefore, I found out what is lambda. Lambda is F of U bar, right? So, therefore, now, therefore, let V equal to F of U bar U. Now we want to say this B does the job. What does it mean? That means for all x in B, F of x equal to x in our product V, right? Now given x in V, but remember V is W perp. Therefore x I can write as some vector in W and a vector a scalar T so that it is T. Remember U is in W perp, right? Therefore what is F of x? F of x is going to be F of W plus Tu, but that is F of W because it's linear and T times F of U. Okay, and this is 0 because W is in kernel. Therefore this is T times F of U. But remember F of U, what is F of U? Therefore it is lambda bar T. Do you understand this? Yeah. But what is inner product x with V? That is this x is W plus Tu and this is lambda U, right? Therefore it is W lambda U plus T times U lambda U, but this is 0 because U is in W perp, right? And therefore this is equal to T lambda bar comes out, inner product UU, which is T lambda bar. These two are equal, right? Therefore, we have proved for all x in w, sorry v, f of x is x inner product and uniqueness as we done earlier. Okay, so pause, review, proceed. So what is the picture we do? Look at this. This is my v. This is my w, which is kernel of f. Okay, and this is going to be my u. So my this t u may be like this. Okay, this is u. This may be tu, maybe t. Sorry, lambda u, where lambda is nothing other than f of u bar. Okay, so you see the geometry. So what all I have to look for is that my particular vector v must be perpendicular to the kernel, and the orthogonal complement of the kernel is of dimension 1 if f is non-zero. Therefore, it must be scalar multiplied plus a unit vector. So I have to find the unit vector. Isn't that idea very beautiful? Okay, please pause, review, proceed. Okay, right. The next thing I want to look at is the following. Okay, this is second observe, use of orthogonal complement. Okay, suppose W is a vector subspace of V and dimension of W is n minus 1. Then we would usually say it's a hyperplane, or a translate of this is a hyperplane. Hyperplane. So the picture is again like this, the same thing. This may be my W and this may be my V plus W. This may be my V and this may be V plus W. This is V plus capital W. Okay. So notice that this is just a translate. So if you think of V as a group or an addition, commutative group under addition, W is a subgroup. This is okay. This is a coset of W. Think of, see, this kind of geometry, the algebraic thinking is also very important. You should not simply work with linear geometries. You should not look at anything else. Okay, very good. Yeah. Okay. Now, what is the question I want to understand? The question I want to understand is, let us look at okay. This is my W, and let's look at my vector x here. I want to know what is the distance between x and W. Notice that if you have learned your metric space, this is nothing other than the GLB of distance between x and W, as W varies over capital W. But this is nothing other than GLB, or if you like, if you are follow standard things, is infimum of what is dxw. Remember, this is x minus W. Norm of this as W and W. Right? So this is the GLB or infimum, but what we are actually going to prove is something very interesting. Okay, we are going to say there is a vector. Okay, there is a vector. Okay, W naught here, so that norm of x minus W naught is less than or equal to norm of x minus W for all W and W. That means this infimum or GLB is attained. It's actually a minimum. Okay, I hope your GLB, minimum, maximum, GLB, they are all very clear. Okay, good. So this is actually minimum is attained. Okay, this is very interesting. Okay, right? GLB is defined, but there will not be a point on W, so that distance between x and the vector subspace W is same as the distance between x and the point W naught. It may not exist, but we are saying it exists. And then we also know how to identify that vector W naught geometrically. Is okay? Do you understand this? Therefore, can we find this? Is there a geometric description? This is a question. Yeah. So how am I going to answer that? Again, let us do that. Okay. So remember, I can write my v. Remember the dimension of this n minus 1, right? Therefore, okay, fix a u in w perp such that norm of u equal to 1. Therefore, w perp is f times u. It's a one-dimensional subspace, right? As we have seen earlier, right? Okay, therefore, now I can write my x as a vector in w plus a tu, where t is in the field u. This is the orthogonal decomposition because my v is w direct sum w perp. Therefore, I can write it in unique way as a vector x as a vector w plus some vector in w perp, but any vector in w perp is a scalar multiple of u. Have you understood? Right. Now, what is that I want to do? Okay, what I want to do is this. Let us look at, so let me call it as a w naught. Okay, let w be anything in w. Okay, now let us look at norm of x minus w whole. And remember, in the inner product space, what did I say? Whenever I deal with norm, it's always easier to deal with norm squared and use inner product. Okay, remember, x minus w naught is less than or equal to x minus w if and only if x minus w naught squared is less than or equal to x minus w squared. That is, a and b are non-negative, then a is less than or equal to b if only if a squared is less than or equal to b squared. How many times I have used it? Okay, right. So let us look at x minus w squared. But this one I can write as x minus w naught plus w naught minus w squared. Do you agree with that? Yeah? Okay. Very good. Now what do I know? What is my w naught? How do I do that? Remember, we already proved something very interesting. What did we prove? We already proved, what did we prove? This w naught is p of x. Because then, remember, this is going to be, then we have proved p of x or pw of x, the orthogonal projection of x onto w. Okay, and this is perpendicular to w. We have seen this, right? Therefore, this and these two are orthogonal to each other. This vector and this vector are orthogonal to each other, right? And we had already seen if okay y and z are orthogonal to each other, then norm of y plus z whole squared is norm of y squared plus norm of z squared. This is what we call Pythagoras theorem, right? Therefore, this equal to norm of x minus w naught squared plus w naught minus w whole squared. Why this is orthogonal to each other? Remember, w naught is in w is in w, and w is a vector space, therefore this is in w, right? And therefore x minus w naught is perpendicular to this. Okay, right? Okay, I'm just recalling the proof which you had already seen, and this is my policy. Do you remember? Whenever I need something very simple thing, go through the proof once again. Okay, this is the way you acquire mastery and confidence. Okay, otherwise you think I had understood, so it should be all right. Go ahead. Okay, good. Have you understood this? Therefore, the unique point w naught is nothing other than pw of x, orthogonal projection of x onto w. Okay, very good. Okay, now I want to find the distance, right? Therefore, the distance, okay, therefore, distance between x and w is same as distance between x and w naught, right? But I know what is this. Okay, x I have written as w naught plus what I have written as t times u. Do you remember? And therefore distance between this is x minus w naught. Therefore x is w naught plus tw minus w naught tu, sorry, tu, that is equal to mod t into norm of u, which is mod t. Have you understood? Therefore distance is nothing other than mod t. Now again think about the geometry. Let me go back to the picture I have drawn. See, this is your mod t. Okay, this is your x minus w naught, and this is our, it's okay, this is your t, this is your u direction. Okay, t may be small or big in modulus, I don't care. Do you understood? Okay, x is the direct sum of these two things. Okay, so problem is solved. So let us understand. Therefore, if I write x as w naught plus t of u, where this is in w direct sum f of u, where u is in w per and norm of u equal to 1. Then distance between x and w is mod t. Okay, this is what the final result. Okay, pause, review, proceed. Okay, let me, yeah, good. Right, let us specialize. Let me take V to be R3 with a dot product and W to be the plane XYZ in R3, so that AX plus BY plus CZ equal to 0. Notice that not all ABC are 0, right? Therefore, if I take my U to be ABC by square root of A squared plus B squared plus C squared, then norm of U equal to 1, and this W is nothing other than U per, right? All vectors which are perpendicular to U. Do you agree with that? Yeah? Okay. Right. Now, let me take a point P equal to x naught, y naught, z naught, okay, in R3, right? What is the distance between P and the point P and W? Yeah? Right. Now, let's look at this one. How can I get mod T? Remember, this vector Tu is nothing other than orthogonal projection of x onto the one-dimensional subspace f times u, right? But how is it given? That is therefore it is p, let me call it u of x, but this is given by x u u, right? Therefore mod t is nothing other than inner product x u. So this also we found out. I should have mentioned that, I forgot. Do you understand this? So we know mod t, but do I know how to find mod t? That's a question I should have answered. Okay, what I am saying is this is the orthogonal projection, right, of x onto this one-dimensional space, right or wrong? Okay. Now we know already, that was our earlier point. The first thing when we talked about is the first thing is orthogonal projection on the one-dimensional subspace spanned by a unit vector. Okay. How is that given? That is inner product x u u, right? But that is equal to tu. Therefore, t must be, sorry, mod t must be this. That is t equal to inner product x u. Yeah? Okay. So we are through. Therefore, this, what all it says is, so take this x, which is a x naught, y naught, z naught, and dot product with the unit vector. What is the unit vector? A, B, C by square root of a squared plus b squared plus c squared. That is ax naught plus by naught plus cz naught by square root of a squared plus b squared plus c squared. Right? Therefore, distance between P and the plane W is given by this. where the plane is given by, the plane passing through origin is given by ax plus by plus cz equal to 0. Yeah. Have you seen this formula from your three-dimensional coordinate geometry? This is the formula, okay, seen in three-dimensional coordinate geometry. Yeah. Okay. Now the final thing, suppose my plane, call it pi, is given by ax plus by plus cz equal to d. That is inner product of the vector, let us call this vector v, with the unit with the n equal to d, where n is the vector abc. Therefore the unit vector is abc by norm of n, which is a squared plus b squared plus c squared. Right? Therefore pi is nothing else than set of v in R3, so that inner product of v with the n equal to d. Okay, this is not zero vector, right? Okay. Now suppose I take a point P, which is again x naught, y naught, z naught. How do I find the distance between P and pi? Again, let us have a picture. It may make your life easier to understand. This is your thing, and yeah, the one we are looking at is, it is supposed to be parallel. This is your w pi. Okay. What I do is you take a point, okay, q, take a point q in pi, okay, and look at pi minus q. That is, you're translate the plane through q. See, remember what is pi minus q? Pi minus q will be set of all points v minus q, where v is in pi, the plane. Okay, this is your pi. This is your pi. Yeah, I claim, call this as w. I claim w is a vector subspace, of course, two-dimensional. Okay, why? Notice that if you start with any vector x in w, which is of the form v minus q, x is equal to v minus q, then notice that x dot product with n, x dot product with n is v dot n minus q dot n, and v is in pi, q is also in pi, therefore d minus d, which is 0, right? Therefore, okay, are you following? Yeah. Therefore my w is contained in n perp. Have you understood? Okay. Right? Yes. Now I want to claim w equal to n perp. How do I do that? Start with any vector. Let us call a vector u in n perp. This u, okay, may let us call some other, okay, z in n perp. Okay, I want to say z is in w. If z is in w, what I have to prove? Any element of w is of the form v minus q. Therefore z must be of the form v minus q. Therefore what should be my v? I can take v to be z plus q. Z plus, not rational numbers, z plus q, the vector, right? Okay, is it in pi? Because v must be in pi, right? Is it in pi? How do I know it is in pi? I have to take dot product with n, but that is z dot n plus q dot n. Remember, z is in n perp, therefore this is 0, and q dot n by definition is d, because q is in pi. right? Therefore, v dot n is in D. That means v is a vector in pi. So what I have shown? I have shown that, okay, if I set w equal to pi minus q, okay, this is a vector subspace, and this is equal to nothing other than n perp. Have you understood? So look at the picture. What all I have done is this. This is my pi, and this is going to be my w. This is pi minus q. Q is a vector here. I just translate. Then it has to pass through origin, right? Because q is in pi, therefore q minus q will be 0 vector. That should also be there. Okay, good. So now just think about what do you think if I take with a p, let us say p, which is x naught, y naught, z naught. Okay, what is the distance between p and my pi? Okay, remember that the vectors, if v and w are vectors in your inner product space, distance between v and w is norm v minus w. These are definition. But if, okay, it's also translation invariant that I had already seen. That is distance between v plus x and w plus x is same as v plus x minus w minus x, which is v minus w, which is distance between v and w. You understand? Therefore, distance is translation invariant. Therefore, I can write p. This is same as p minus q and pi minus q. Yeah. Again, you should notice this is by definition GLB of, okay, distance between p and some vector, okay, z in pi. But right, but this GLB is same as GLB of distance between p minus q and pi z minus q as z varies for pi. You understand this? Each one of these numbers is equal to this number. Therefore, GLB of this set of real numbers is the same as the GLB of this set of real numbers, because each number here is the same as this number, corresponding number here. So the sets are the same subsets of real numbers. Okay, therefore their GLBs are same. Okay, these are the small things you should learn, because these are, okay, because time constraint, teachers may not explain these things well. Have you understood? But no, this is a vector subspace. Therefore, we know how to find the what? The distance between p minus q and pi minus q. This is nothing other than the inner product of, this is nothing other than the modulus of the inner product of p minus q with n by norm n. Okay, if you want, okay, this is the very general case. Okay, I am still working with the very general case. I am not working with R3 or anything. If you want, you can do that, right? But what is this? This is same as inner product of p. Let us call this a unit vector u. Therefore, inner product pu minus q inner product u. Yeah. Do you understand this? This is in modulus. Yeah. But this we know what it is. This is, see, q lies in pi. Therefore, what do I know about q inner product with n? That is d. Therefore, q inner product with the u, that is u will be d by norm of n. Therefore, this is minus d by norm of n. And this is also again p with n by norm of n. Okay, this is a modulus. Therefore, I can take norm of n outside. Therefore, it says Pn minus d modulus by norm of n. This is the distance between p and pi. Okay, pause, review, proceed. So distance between p and pi is modulus of the inner product of p with n minus d by norm of n, where pi is set of all vectors v and v such that v inner product n equal to d, some constant. Right? Now specialize to R3. So my pi is given by ax plus by plus cz equal to d. Therefore my n is abc. Right? Now the point I want is x0, y0, z0. That is my point P. Okay, therefore what is the distance between my P and pi? This is take x0, y0 with n, therefore ax0 plus by0 plus z0 minus d modulus by square root of a squared plus b squared plus c squared. I'm sure you have seen the formula in three-dimensional coordinate geometry, right? Yeah. So, but the formula which I arrived is true for any finite dimensional inner product space, whether it's over R or over C. Okay, if you define the hyperplane to be, take a non-zero vector n, define the hyperplane to be inner product of x with n equal to some constant. Okay, so remember it could also be complex constant. Did you see that? Okay, now the distance of any point P in the vector space B is given by this. So inner product Pn minus d by norm of the vector. It's a very beautiful formula, right? We are not stuck with R3 over R real vector space. All these things works. Only is the modulus. I hope you enjoyed this lecture. This is beautiful geometry. That is why I call linear algebra is n-dimensional geometry, and real inner product space of dimension 2 is a model for Euclidean geometry. Over R real inner product over three-dimensional space is a model for three-dimensional coordinate geometry, and therefore Rn with the dot product should be intuitively n-dimensional Euclidean geometry. I hope you all enjoyed. We will meet again.